Okay, so it is my very great pleasure to introduce Dr. Henry Astley for today's seminar. Dr. Astley is an assistant professor of biology and polymer science and a core faculty member at the Biomimicry Research and Innovation Center at the University of Akron. He got his BS from the Florida Institute of Technology in Aerospace Engineering before switching over to biology and getting a BS and MS from the University of Cincinnati, and then a Ph.D. From Brown University. His research focuses on the biomechanics of animal locomotion, primarily in snakes and frogs and early tetrapods. And his work combines multiple techniques, including high-speed video, inverse dynamics, some in vitro muscle testing, as well as some construction of biomimetic and robophysical models. So today he's going to talk to us about some of his exciting work on multi-articular muscles, which I'm personally really looking forward to. So welcome, Henry, and please take over.
Great. Thank you very much for that lovely introduction. It's wonderful to be here. It's a great series of seminars, and yeah, I'll be talking about my recent work on multi-articular muscles and a little more mathy, given the focus of this seminar series. So, without further ado, let me get started. Let's hope this works properly. Alrighty. Is everyone seeing the full front page thing?
Yeah.
Alrighty, fantastic. Cool. So, I am particularly interested in multi-articular muscles, and so morphology is a crucial part of how muscles interact with the world. Muscles are complicated tissues that are the primary motor of most movement in animals. There's a very few exceptions, but generally speaking, if it's moving, it's muscle. It has all sorts of dependencies on length, on velocity, activation, etc. And muscle wants to shorten. Muscle, if you turn a muscle on, it will try to shorten unless something stops it. And in order to convert shortening into various useful things such as joint rotation, limb extension, things like that, animals have a variety of rigid and soft body structures. Skeletons, whether they be internal like ours or external like an arthropod, or soft skeletons like a worm or a squid. These all convert the shortening motion into other types of motion. And in doing so, the geometry and the mechanics of the anatomical system and the anatomical arrangement of the muscles strongly influences how the muscle functions. The simplest example is a monoarticular muscle, or largely so. Biceps isn't totally monoarticular, but we'll fudge it. It's a good example where the distance of the muscle attachment from the joint determines how much torque it's going to generate and how rapidly it's going to shorten. The attachment further away, it's going to generate more torque but move more slowly. Closer to the joint, less torque, more quickly. Things get a little more complicated when it crosses two joints in a much more substantial way, such as this muscle in a horse. There's a variety of these biarticular muscles, because they cross two joints, in a wide number of species, and they have a lot of different functions. They can function for control, they can transfer power, they can function as a fixed length strut, or they can actively shorten or actively lengthen. And they're particularly common in the limbs. We have a whole bunch of them in our limbs, as well as most other tetrapods. But they're considerably more complicated than your simple lever system, because now it crosses two joints. However, some systems are much, much more complicated, where a given muscle will cross large numbers of joints, 3, 4, 10, 20 joints. And this often involves having many, many muscles with many, many attachments, as you can see here in this diagram of a barn owl, I believe, neck from Bowman's et al. 2015. So these systems are quite complicated, and this brings up the question of how does anatomical structure and the arrangement of these muscles relate to function? What's the benefit of having a multi-articular muscle system, which I'm defining as a muscle that crosses more than two joints? What's the benefit of this compared to just having a bunch of monoarticular muscles crossing these same joints? And what's the consequence of a muscle that crosses 3 versus 5 versus 7 versus 15, so on and so forth? How does this relate to function? How does this relate to how the organism works and the mechanical output of the system? And so these systems are actually fairly widespread, perhaps not as common as biarticular muscles, but they're seen in bird necks, they're seen in tails of species like primates, as well as lizards. Our own fingers are sort of a multi-articular system. All the actual muscle is down here in either the palm of the hand or in the forearm, and it's these long tendons that control grasping. So they're a very widespread system. And my particular focus organism, snakes, have a very complex version of these. They have a large number of muscle types. So each of the numbers in this picture from Gask of a horned viper muscle system, each number corresponds to a different muscle group that is repeated iteratively, one of each of that muscle type per vertebra. And they can be anything from monoarticular to spanning dozens of vertebrae, in some cases nearly 50. So it's a very complicated system. As I said, they occur in these overlapping groups. So if I have a muscle like this semispinalis spinalis here on the top SSP, hopefully y'all can see my mouse. It goes from number 1 to vertebra 19, and then there'll be another one going from 2 to 20, 3 to 21, so on and so forth, overlapping, which in turn are overlapping this little multifidus down here, and then they're connecting to the longissimus dorsi over here, which again, series of overlapping systems. Some of them, the span is mostly muscular. Others, it's mostly tendinous. And there's minimal data for all but a few muscles and all but a few species. So a lot of stuff is left unknown in these. So here's an example of some of these differences. So on top is a vine snake, a highly arboreal, very thin-bodied species. The bottom is that same horned viper. And you can see that not only do the muscles span different numbers of vertebrae, but they have different proportions of muscle belly. So here the vine snake has relatively small muscle bellies of the iliacostalis with long, long tendons, whereas the viper, it's mostly muscular for the same system. So what's the consequence? Why have these different spans, these different tendon ratios? So what's actually known? Well, people have been intrigued about this for a long time. The first note actually goes back to a dissection of Vipera caudasona, for sound tail, a rattlesnake brought to London from the New Virginia colony in 1682. There's been anatomical descriptive work from previous authors. Gask published quite a lot of this. However, quantitative details exist only for a few species. So we don't have a huge wealth of knowledge of how these spans and tendon ratios differ among species. Rubin did some work suggesting that the tendinous span would be advantageous for lateral undulation, but impede constriction strength and vice versa. Bruce Jane's 1982 paper and the subsequent reanalysis with Jessica Tingle, who will make an appearance later in this, albeit indirectly, via me talking about her work, analyzed the semispinalis muscle, looking at a huge number of species, but just this one muscle, and found a powerful link between the semispinalis span and arboreality, particularly tendon length. Most of the studies in other species have taken advantage of the relatively low number of degrees of freedom to use computational methods. So they've run it all through a computer, get exact solutions, but they don't have general principles. So we're still missing some of these general principles because humans don't vary in how many finger joints they have. Once you have your explicit solution, you're pretty much done as far as humans, but not so for other species. Another recent paper used inverse dynamics methods to try to determine the mechanical consequence, modeling them as a elastic string across joints. And their math worked, but when they tried to do it experimentally, it failed. And the reason is that if there are fewer muscles than joints, then the system is unconstrained. It can adopt a wide variety of geometric postures of series of joint angles that still satisfy the same muscle length or string length in the case of this example to the right. And given that, it will naturally adopt the posture that has the lowest potential energy. So as you can see here, as soon as there's two joints free to move, it starts to sag and adopt the lowest gravitational potential energy system. Excuse me. So, one of the systems that we've used to examine it, and what we're going to start with, is cantilevering. So cantilevering, like you see in this snake in Peru, Imantodes secnoa, or Senkoa, sorry, is a crucial part of arboreal locomotion, and many, many snakes are specialized for this in arboreal habitats, particularly this one. This particular species has the longest tendon span of any snake that's yet been described. A single semispinalis muscle of this spans 50 body vertebrae, an eighth of the snake's entire length per muscle, and almost all of that is tendon. It has a lot of other features that make it good for this sort of analysis. It's quasi-static, the accelerations are pretty minimal. It's wobbling around there a little bit, but we can generally assume accelerations are negligible. We do have EMG confirmation that this particular muscle, the semispinalis, this dorsiflexor, is the primary muscle used in this activity. There's extensive comparative data on it, the aforementioned Jane and Tingle papers. There's extensive comparative data on performance in snakes, so we can compare both performance and anatomy. And as I mentioned, it's crucial to arboreal locomotion. You have to cross between trees or between branches quite often. So I came up with this relatively simple model. All models are wrong, but some models are useful, and I'm missing certain things like a head, which is sort of important for an animal, but I'm trying to get at general principles and avoid some of the complexities and nitty-gritty of the real snake and sort of build outwards from there. So I created this system of identical joints of a certain mass M, length L, and the muscle attaches with a constant lever arm A, and all the muscles are offset in this image just for clarity. The actual muscles all have the same lever arm. They're all piled on top of each other, so to speak. This is actually true for the snakes. The anterior tendon of this muscle is bundled into a very tight little column. Someone saying losing audio. Are we good? No? Okay. All right. I'll keep going. It's being recorded. So, anywho, we're ignoring the head and the cervical musculature because it is complicated. And we're assuming that the ball and socket joints in the vertebrae are resisting the shear and horizontal forces. So the vertebrae are compressing to resist horizontal forces, and the vertical force is effectively countered, again, by the geometry. So all we care about is the moment, the rotation at the joint. So, thus, at any given joint, some combination of internal musculature across these N muscles resists the moment imposed by gravity. And the span of this is P. We're going to use P as this generic variable for how many joints does a muscle span, regardless of whether it's purely muscular or purely tendon. For now, we're going to stick with purely muscle. So, external moment is actually fairly simple. Anyone who's done beam cantilevering is familiar with this. It's your nice parabolic system where this is basically mass per unit length, and it goes up to the square of the number of joints. So this is how much any given joint has to resist due to gravitational loading as it sticks out horizontally. If it were to go up or down, it's just the cosine of this. So we'll ignore that. We'll treat horizontal as the most difficult, and so we'll go with that. And we can analyze this using a common engineering technique called the method of sections. Those of you who are engineers and have taken statics are either bored now or having flashbacks to your undergrad and your exams of finding the forces in all of these truss structures. The idea behind this is actually fairly straightforward. If I have a system like this and it's not moving, it's static, then I know that the sum of all the forces must be zero and the sum of all the moments must be zero. And that's true for the attachment points at the ends and where the load is, but you can also slice this thing in half virtually and run the same analysis and say the sum of the forces in the x, y, and the sum of the moments must be zero, otherwise this particular part of it would be moving. And you can do as many slices as you like and solve for all of your individual elements. So we do this, we treat this system fairly straightforward, and the simplest method is monoarticular. So if I have a monoarticular system where each muscle just connects to the next vertebrae, then the muscle force must be equal to the external moment. Pretty straightforward. So if that's our baseline, and so that goes up with I squared. But now, if we have a simple biarticular muscle, for the first one, it's the same, because only one muscle spans the joint. But at the next joint, at joint number 2, hopefully y'all can see my mouse, the second joint along, then there is still you have this higher force. It's the 4 is the coefficient, but you're still getting this contribution from the first one. So this second muscle only has to sort of top it up. It has to add a little bit, so it adds 3, and then the same thing happens again in the next one. You've lost the contribution from the first muscle, but you're gaining that contribution of 3 from the second one, and so now you only have to add 6 to top it up and reach that goal of 9. So on and so forth. You can go along the system and get your nice series of coefficients. And so what I mean by coefficient is, for all of these systems, the force at any given muscle will have this same coefficient at the beginning of mass times gravity times length divided by twice the lever arm. And then this I here, this is this coefficient. And so you can see how the coefficient rises. Here it goes up, and by joint number 10, it's at 55. I can repeat this for a span of 3, a span of 4, so on and so forth, and come up with a general formulation. And the general formulation has to be piecewise, because you essentially have 2 regions. You have the region of where you're just adding muscles. You haven't reached the length of one span yet, so you're just adding. So that's this portion up top here. And then after you've gone through the full span, well, now every time you move back a joint, you're losing one and gaining one. And that's the second part of the equation. But this is very tedious and annoying, so we make MATLAB do it. And so here's what we get when we throw it through MATLAB. So on the left is for shorter joints, going from monoarticular, p equals 1, all the way up to 10. And then the left one, we're going a much larger, the right one, we're doing much larger articulations, 10, 20, 30, 40. And we can approximate this reasonably well using this quadratic equation. It's not perfect, but it's a pretty good approximation, especially for long spans. So what this does show is that as you have more and more multi-articular muscles, each muscle only has to sort of top up the others, and it's getting all these contributions from all these other muscles. So it has to generate comparatively less force, which is not that surprising. But I don't trust my own math. I don't trust myself not to drop a minus sign somewhere. So I made a very simple mechanical model with joints of 3D printed plastic, muscles of Kevlar, where I would measure their force with a little Pasola gauge, a little spring scale, and a span of 4 joints, and compared what I expect to what I got. And what I got was probably what's going to be the best R-squared I've ever gotten in my career for anything, and probably ever will again. I have no hope of ever getting anything like this from biological data, but we got a pretty good estimate. Everything falls reasonably closely within the line. The intercept does not differ significantly from 0. The slope matches the mass times gravity times length times lever arm of these systems. So all good. Especially for something made of 3D printed plastic, twine, eye hooks, and dollhouse hinges. So, weirdly enough, for little doors in the dollhouses. You can buy amazing stuff on eBay. So, This, of course, brings up the question of, okay, well, when is failure going to happen? How does this relate to actual performance? The muscles are contributing less. When does the system fail? What determines how far a snake can reach? And contrary to expectations, it's not going to be when all of the muscles are maximally active. Many of these early muscles will be nowhere close to their maximum load. Instead, it'll occur at the point where the amount that the muscle needs to top up the load exceeds its capability. So if I go from the 49th joint to the 50th, I've lost the muscle that started way back where, however much my span is. I have to add a little bit to top it up. If that little increment, if that one muscle exceeds that particular muscle's capability, that's when failure occurs. So it's that sort of the weak link in the chain. Each muscle has to bear an increasing load, and it's when that final muscle can't handle it. All the others are still well submaximal. It's that one where you cross from minimum to maximum. So, if we assume that the snake has a constant muscle volume, which we have to, because otherwise, well, yes, if I have more span in the same cross-sectional area, then the snake is just getting stronger and stronger and stronger and thicker. So that's not really a fair comparison. Instead, we're saying, okay, the snake has a certain muscle volume, a certain cross-sectional area per joint, and it's distributing this differently. It's either having all of that cross-sectional area in one joint and it's monoarticular. If it's crossing two joints, it has to split that cross-sectional area into two. If it's crossing three joints, it has to split it into three, so on and so forth. And so we did a very simple version where the isometric force, P naught of a muscle, is per cross-sectional area times the cross-sectional area divided by the span. So as you have more span, you have to divide your cross-sectional area up more in order to account for this. And so this should give us a reasonably good estimate of when failure occurs. And the answer is, weirdly enough, performance actually gets worse as muscles become more multi-articular. It's a pretty steep decline, too. So the reason is that although the multi-articular muscles are beneficial, what you sacrifice in per muscle cross-sectional area from subdividing it is actually higher. So you're getting this benefit, but it's not enough to offset your losses. But this doesn't match up with what we see in nature. In nature, highly arboreal species have really long multi-articular spans and really amazing cantilevering ability to cross gaps. And the issue is tendons. So many of these species have extremely long tendons with a relatively constant amount of cross-sectional area for these. And so if you use a tendon, well, now you can have your cake and eat it too. You can have this extremely thin tendon that basically takes up a negligible portion of your cross-sectional area in order to span as many joints as you want, and just have your muscle cross-sectional area divided across a much smaller number. So here we have sort of an example where the muscular portion is only spanning two joints. So it's your total cross-sectional area over two, but the tendon can span 8. I could just extend these green lines as far as I wanted, 10, 20, 50, whatever. So this basically lets you have the multi-articularity without paying as much of a cost. Theoretically, a muscle could span a single joint and have a super long tendon if we wanted. So now we have this additional variable. We can look at the consequence in terms of gap span relative to a monoarticular system. So the blue plane is a monoarticular system with no tendon whatsoever. And we can see that, as before, increasing your span always reduces your performance, but having more tendon dramatically increases it. So all you need is a fair bit of tendon to compensate for these losses, and you have substantial performance improvements. This, in turn, does match what we see in the animal. But why not make it mostly tendon? As I said, you could have all your cross-sectional area at one joint and the rest be tendon. The problem is muscle can only shorten so far. Most muscles are shortening 30, 50% maybe, depending on the individual and the behavior that's going on. There's some exceptional cases, but muscle can only shorten so far. And The further away you are from the further your lever arm, the more shortening you have. But that's just the muscle tissue. The tendon, even if it is stretching, it's not stretching that much. So if you have more tendon for this span, in order to achieve the same vertebral curvature, all of that length change has to happen in the muscle. And so theoretically, having more tendon means that to achieve the same behavior, your muscle has to go through more length change. Or correspondingly, if your muscle can't go through more length change, then having more tendon limits your range of motion, one way or the other, however you look at it. So this gives us a trade-off. We have this linear trade-off going from sort of the orange line for the relative range of motion compared to a monoarticular system or a system with with no tendon, and the benefit of tendon in this blue line. And it turns out when you map a bunch of the snakes onto this, they're all way over here on the right side with high fractions of tendon and high or low relative range of motion. So this suggests that the benefit of the tendon really is large, or that the range of motion isn't limits aren't that important. But this leads to the question, well, what is the actual range of motion? What is the actual lever arm? How far is the joint bending? And how much strain should the muscle actually have? Because if the muscle arm is short, or the lever arm is short, maybe the muscle just isn't going through that much length change. And so you don't need to worry about losing too much length for the tendon. So the problem is nothing is known about lever arms and snake muscle at all. Not a single paper. There's 2 papers out there that look at the cross-sectional areas of the muscle, and they'll usually make an assumption. So Jane and Riley made the assumption of the top of the neural spine as the lever arm for this particular for the semispinalis spinalis, but there's no actual quantification of the lever arms of various muscles in snakes. It seems like a simple question, but no one's touched it. And so we decided to engage with it. And this is part of my recent career grant. And I'm working with Dr. Jessica Tingle. She's the postdoc on this grant at the moment, and she's doing fantastic work. If you're looking to hire someone. So Jessica has been working on muscle lever arms in corn snakes. There are model snake species. And what we did was we DICE CT scanned them. So we euthanized the snakes, we stained them with PMA based on Paul Gignac's DICE CT method, and then micro CT scanned them. So this gives us these divisions where you can actually see the borders between the muscles. We did have a size series and we got scaling. Most of the things involving the vertebra itself were largely isometric. The lever arms were mostly isometric. Cross-sectional area of the muscles was actually, in many cases, allometric. The full details are in the paper, which will be coming out soon, as soon as we get around to submitting it. It's close, final draft. Anyhow, so Jessica segmented out the muscles in ImageJ using the Fiji system for dealing with CT scans and calculated the lever arm 3 different ways. And I'll go into why we did this. So the simplest version of the lever arm that most people would be familiar with would be figure out the centroid of the muscle area and compute its distance from the joint that's being moved, which would be the cotyle condyle sort of ball and socket joint these animals have at their vertebra. And so the X component would be the lever arm for lateral bending. The Y vertical component would be the lever arm for dorsal flexion in this case. The problem is this makes 2 assumptions. It assumes that the muscle is oriented purely parallel to the body axis and that the muscle attachments are similarly parallel, that basically everything is going along a line with that black dot in the middle of the muscle. And the problem is both of these are wrong. So it's simple, but it's wrong. But the question is, how wrong? Is it a justifiable simplification, or do we really need to do something more complicated? So we did something more complicated. The actual definition of torque is the cross product of the lever arm and force, the vector cross product. And so the result of this cross product is itself a torque vector. And the components of that torque vector, shown here in this matrix, are the torque in the dorsoventral, lateral, and torsional direction. So dorsoventral is up and down, lateral side to side, torsion would be twisting. And so the great thing about this is it incorporates the fact that the muscle fibers are at an angle relative to the body axis, as well as the fact that the attachments similarly are so. And so the force, in this, you see the force has an X and a Y component, but you should also visualize a Z component sticking out of the screen towards you. And in fact, that's the largest component. FZ is huge compared to FX and FY. So, the good news, both of these methods, the cross product and the simple distance method, have very similar results. They give lever arms for the they give lever arms for lateral and dorsoventral as plus or minus 10% of each other. So they're pretty consistent. So there is angle, but it doesn't seem to matter that much. And most of the results are what you'd expect. Muscles that are on top of the vertebrae have high lever arms for pulling the body upwards for dorsal flexion, and minimal moments for moving the body side to side. Vice versa for lateral muscles, as you'd expect, and we generally get results that are consistent with EMGs. Generally. Then we have a problem. The problem is this system, this cross-product method, essentially assumes that all muscle is occurring at a single joint. So it essentially assumes that whatever joint that we are picking as the joint is the only one that's moving, and the rest of the snake's body is fixed. And this becomes a huge issue with muscles like the iliacostalis. The iliacostalis is this muscle that is traditionally regarded as deflecting the body downwards, and electromyographic evidence confirms this. But if we assume the joint is over here on the posterior side of the snake, on the left of the screen, then it flexes the snake ventrally. If we assume the joint is up in the anterior portion of the snake on the right of the screen, it actually flexes the snake dorsally. And that's bizarre, and it shouldn't work. And ultimately, the reason is that it is a mathematical fiction, that it's a snake. It doesn't move at just one joint. It moves at lots of joints. That's sort of the whole point of a snake, is having lots and lots and lots of joints. So we need a method that explicitly incorporates the multi-articular nature of these muscles. So this resulted in a lot of suffering at the whiteboard, staring at spirals to the point that you'd think we're some sort of weird conspiracy theorist. And the great thing about this, though, is we can make some simplifying approximations and come up with an equation. We assumed that the vertebral column was bending evenly, so every joint has the same angle, and so as a result, we can model the vertebral column, LV here, this sort of dashed dark gray line, as the arc of a circle. But for muscles like the iliacostalis, the posterior attachment point and the anterior attachment point, DP and DA, might be different distances from the vertebral column. And in fact, that's, with the exception of one muscle, that's the way it is for all of the snake muscles. So instead, it winds up being an Archimedean spiral. And to figure out the length of the muscle, we have to figure out the arc length of a segment of an Archimedean spiral, which results in this fairly nasty equation down here. So, good news, though, is we can simplify this equation because it essentially boils down to two parts. The top part, in green, is what we call the arc approximation. And so the length of the muscle is, in this case, being approximated as a circular arc with a distance that is literally just the average of the two distances. It's dA plus dP over 2. So that's basically approximating the whole thing as a circular arc and ignoring this whole spirality. And then down here in blue is what we call the spirality adjustment. This is the adjustment to the length that you have to do to account for the fact that, in fact, dA and dP are different. For most snake muscles, this spirality adjustment is trivial. It adds less than 1 or 2% to the muscle length, or changes it by less than a couple of percent. So we can get away with ignoring it, And if you ignore it, it actually simplifies down to our simple distance approach, where it's based on the average distance in a particular plane. So imagine if you're looking at the snake from the top down, and this muscle is a lateral flexor. This is just the average distance of the muscle from the vertebral column, dA plus dP over 2. So that simplified things tremendously. It also got rid of this annoying problem with the iliocostalis in an elegant way. It also gives us this lovely insight, which is the torque of the muscle is constant across all joints, or nearly so if we include the spirality. But the muscle shortening is essentially diluted across multiple joints. If I shorten the muscle by X millimeters, if it spans more joints, then each joint will deflect correspondingly less. And this follows from conservation of energy. I'm doing work at all the joints, and the work is being done by the muscle. So if the torque is always the same, if I'm doing it across multiple joints, I have to dilute the displacement portion of work. Anyhow, the iliocostalis actually is resolved in a peculiar way that's called asymmetrical buckling. So if you've ever played with a meter stick and pushed down on it, you've noticed this peculiar phenomenon called buckling, where the meter stick initially compresses, to us an infinitesimally and invisible amount, but after a certain force, it suddenly bows to the side, seemingly at random. This is a phenomenon called buckling. And it occurs when the energy to hold the straight position is suddenly more than the energy in the curved position. And so this is what you see in this lovely little animation that I pulled from Wikipedia. So the red is the energy landscape. The vertical is how much energy. The lateral is the curvature. So the horizontal axis is the curvature to one side or the other. And so when you first start loading it, the energy minimum is the bottom of the trough, and it's right in the middle. But then once you pass this point, this supercritical pitchfork bifurcation, now the middle is an unstable equilibrium point, and any slight deviation will cause your sort of metaphorical ball to roll off to the left or to the right, which is why when you push on a meter stick, it bows to the left or the right, seemingly at random, as it's going through this supercritical pitchfork bifurcation. And it's symmetrical, which is why it's random. But this system is not symmetrical. So we have our iliocostalis, our muscle in red, LM. We have a vertebral column, LV, and it's attached at two different distances, DP and DA here. So it's crossing the axis, just like you see in the real snake. And we say, okay, what happens if I deflect the vertebra down or up, maintaining it as a constant curvature? So fortunately, as ugly as this looks, it actually turns out to just be the law of cosines for figuring out the muscle. And it gives us this equation. We can plug it in, graph it, and we get this graph here on the right, where the horizontal axis is curvature to the left or to the right, and the vertical axis is muscle length. And what we see is that by offsetting these attachments, we've created an asymmetrical system, where in order to pitch upwards, you have to stretch the muscle just for a bit. Once you get past a certain critical point, then further muscle shortening will cause it to deflect upwards. But if you're starting in a straight position, or nearly so, anywhere on this rightwards down slope, then the muscle will deflect the body downward. So it creates this asymmetrical buckling. So now we've figured that out. We've got our lever arms now, and we can do some estimates. And we've got some estimates I've pulled here from our largest corn snake. We've got dorsal lever arm, lateral lever arm, and the tendon ratio for the semispinalis, which is a dorsiflexor. It's pulling the body upwards, as well as repeating this for a pure lateral flexor, the longissimus dorsi, which has basically no dorsoventral aspect. It's just bending the body sideways. And we know from ex vivo measurements from snake vertebra manipulations, we have a range of motion dorsally flexing up to 10 degrees per vertebra. Laterally, it's 18.7. In vivo, we have one measurement from Bruce Jane's 88 work on concertina locomotion that gets to 14.3, so pretty close. And from these, we calculate maximum strain. And so what we get is maximal strain is about 50% for both of them in their respective motions, using either maximum vertebral range of motion, observed in vivo range of motion. And so these are all reasonable. They're high. A muscle with a 50% shortening is on the high end, but it's not something that would make me pause and reevaluate the whole project. It's not like it's 150% or 3% or something like that. We're in a reasonable approximation here. This is something I'm not looking at this and going, something's terribly wrong. And we do have some strain of about 30% for these muscles, from the paper Jurastovsky et al. That was just published this year, but crucially, that strain data is from post-mortem bending. The animals were euthanized, bent maximally laterally, and then fixed. And so that does not necessarily represent what's going on in vivo. But we're getting something that's reasonably plausible. And so to wrap up, what we've been doing here is actually looking at this middle portion. So on the left here, you've got the muscle as a physiological tissue with its length tension and force velocity relationships and what have you. And on the right, you have the external loading conditions, gravitational loading from cantilever, but also other conditions. And anatomy is sort of the link between the two. The muscle does something that translates into anatomical displacement of the skeleton moving, which in turn relates to external loading conditions, the animal imposing load on the environment, or conversely, the environment imposes some load that's transmitted through the anatomy to here's the per muscle load. The problem is both of these are very poorly understood. We sort of solved the middle part of this without going either end first. In all fairness, it's because it's simpler, but yeah. So we have started to explore the muscular side of things. So as I mentioned, this is from Jurastovsky 2022 from my former PhD student, Dr. Derek Jurastovsky, who is now a postdoc at Penn State. And we looked at the sarcomere length of snake muscles across a huge number of snake muscles and a size range of snakes, and found, this weird consistency where they're all on the descend, they're at the straight configuration. So when the body is straight, that's where these little symbols are, and the ends of the color bars are where it's at maximum bending left or right. And they're all weirdly consistent across all the muscles. If you did this within a human arm, you wouldn't see anywhere near this level of consistency. So why? We don't know. This is a constrictor, so maybe this has something to do with its constriction behavior, but maybe this has something to do with the multi-articular nature of the muscles, because this sort of level of consistency is weird. So, other loading conditions, on the flip side, snakes do more than just cantilever, obviously. Lateral undulation, concertina locomotion, constriction, striking, all of these will produce different patterns of loading, different patterns of external moments along the body. And how does that relate? So all of the stuff in the beginning was all based on cantilever with this external load that rises to I squared. But what if that's not the case in, say, lateral undulation or constriction? How does that change the results we see? And so this method can be applied to assess the consequence once we know those external loads. That's the trick. Now we need to find those external loads, which is one of the things that we're currently working on. So to wrap things up, and hopefully I'm not too far over time, for cantilevering, multi-articular muscles alone are beneficial, but the benefit is less than the loss of cross-sectional area. The key is tendon. You need surprisingly little tendon for it to be beneficial, for the benefits to outweigh the costs, and substantial tendinous portions can confer tremendous advantage for cantilevering ability. However, they also result in lower range of motion or greater muscle strain, however you want to look at things. Fortunately, it seems to not be a terribly big issue for most snakes. We found that the lever arms of these systems can be simplified with minimal loss of accuracy. Despite all the complexities of the cross-product method and the multi-articular method, it turns out that if you do want to simply go to your local museum and do a comparative version of this by slicing a bunch of snakes in half with a razor blade or a scalpel, that will give you good results. It won't be perfect, but it'll be close enough that the inaccuracies will be less than, hopefully, whatever you pick up from multi-species comparisons. And it does lead to some interesting behaviors like asymmetrical buckling. It has potential benefits for robot snakes. So to date, as far as I am aware, no one has actually built a robot snake with multi-articular muscles. There's a simulation, but no one's actually made one of these things. And the predictions should still work. It's just if you have a motor with a cable, these equations will produce the cable results. However, there are some differences in a robotic system that could be to the robot's advantage. So in real muscle, metabolic cost depends not just on cross-sectional area, but also length. You have to activate the entire length of the muscle in order to generate, to keep the force going. But a robot, torque is the primary determinant of current cost. So this basically your span or your muscular span would not matter. Similarly, increased span would not necessarily result in decreased force. You could just have a one motor per segment and a cable for the rest of it. So essentially a tendon ratio of whatever the maximum is. And on the flip side, though, motor torque per unit mass could be a big limitation. So motors are heavy compared to muscle. So this could seriously impact things. And finally, the control implications could be quite complicated. Or maybe not. I don't know. That's one of the things we're looking at. So how do you control these multi-articular systems? Especially when you don't have a nervous system like a snake. So, open questions. There's just too many to fit on a single slide. I mean, there is more that is unknown with snakes than is known in the mechanical sense, and there's just so many questions that you can think of. So, with that, I will wrap up. I'll give special thanks to Derek and Jessica for all of their work on this, as well as the NSF for funding. And the early portion of this was also from a symposium talk that was funded by SICBI, the Society for Experimental Biology, and the Company of Biologists. So with that, I will wrap up and open up to any questions.
So fantastic presentation. So thanks a lot, Dr. Astley, for the great talk. We have time for questions. So
oh, I didn't go over time.
Not
That's amazing.
Yes, please.
So I have a question. I'm very interested in the muscle physiology implications of this, and you sort of touched on it a little bit at the end, right when I was thinking about it, which I thought was great. But I'm wondering what you think about the crazy consistency in the sarcomere length.
Mm-hmm.
And the fact that, I mean, you mentioned when you have a lot of multi-articularity and the tendons very long, the muscles have to go through a much greater strain range. The position of those, and especially the position where it's in when it's maximally contracting, really nicely spans the plateau. And I mean, that seems like a pretty good explanation, right? I mean, have you done any work beyond the sarcomere level to look at like the muscle fiber?
Not yet. It is on the to-do list. Next step is actually getting in vivo muscle strain using fluoromicrometry. Thanksgiving and Christmas and SICBI caught up on us, so we had to boot that until spring semester. But we're going to start implanting beads in snakes come January and hopefully get some direct measurements of muscle strain. And then following that, actual muscle physiology, force, velocity, activation, deactivation. I'm not sure if it's proper to call them work loops because they very well might not be cyclical. Snake locomotion often is very acyclic, which can make all sorts of weird things happen with work loops. In fact, Rich's paper is cited extensively in that section of the grant proposal. Your mouse asymmetrical sawtooth paper. So yeah, yeah. The other thing with I guess I'm a little reluctant to go too far with the descending limb because this is just one species. For all I know, I could grab a garter snake and get something totally different. Or maybe it's just one thing that we do see in these mussels. I didn't go into it in much detail, but the muscle span variation is mostly in the quote advanced snakes, the colubroids. Boas, pythons, and that lot don't have as much variability. And so why? Yet another, who knows? So, yeah. Mm-hmm.
Thank you.
Awesome. I see a raised hand.
Yeah. So so when I was looking at your sarcomere links and overlaid what looks like the sort of standard frog,
Right,
single fiber. Do you actually know filament lengths in these mussels? Because the dogma is, of course, that thick filaments in vertebrates are almost always the same length, but thin filaments are not. And for instance, if you were looking at a lot of mammalian mussels, because of the longer thin filaments, the curve is actually shifted over. So, and it's true, like in the birds that we looked at, for just a single muscle, we have filament lengths. Optimal sarcomere lengths are more like 2.4. So it shifts your curve over.
That's
So
a
it
surprisingly big
adds to
amount.
your workload, but
Yeah.
you ought to consider trying to get some, you need a good collaborator who can do TEM on them and get some measurements of the filament lengths.
Yeah, I definitely want filament lengths for these as well. Unfortunately, literally last faculty meeting was the TEM is broken, and how much do we pay for either a new one or a new service contract? So, so yeah, I definitely need to find a collaborator to get some TEMs of these mussels. But I still have all the mussels in little tiny jars.
Okay, great. Yeah.
Yeah. Thank you. Yeah.
So we have a further question from the chat. Let me see if I can read it well. Hi, Harry. Thanks from Dylan Wainwright. So, hi, Harry. Thanks for the talk. So cool. Maybe your point about tendons kind of nullifies this question, but I'm curious about the cross-sectional area of snakes. I'm no snake biologist, but my sense is that snakes are thicker in the middle and thinner at the end. Is that increase mostly muscle? And if so, is the increasing muscle size cross-sectional area relevant in what you're thinking about and how it might be changing things? And how different is that among different snake ecologies? Thanks.
Yeah, so excellent question. One thing that we did find so far is that the data that we have for the lever arms, cross-sectional areas, etc., is just at 3 points. It's just at 50%, 25%, 75% of body length. And at those points, we don't actually see terribly much difference. If there are significant differences for one or two muscles, they're very small. And most of them, there's no detectable difference. So it seems like the middle half of the snake seems to be reasonably consistent. Of course, things do get different as you get closer to the head, closer to the tail. How different are they? We don't know. That's a whole unknown sort of area. Just from external morphology, there seem to be differences with ecologies. Certain species seem to be more even in length than others. But whether this translates to muscle cross-sectional area or is this just ribs or vertebral anatomy, we don't know. So yeah, we have a very limited data set, and I don't want to try to generalize too far, but those are definitely real potential questions, and something that, again, one of the good things that we found by finding that several of these things don't matter is that someone interested in these could just, go to the museum and find a bunch of specimens that nobody cares about you cutting in half anymore, and and get some data from those, where you could get way more data for way less effort than it takes to dye CT stain something and micro CT scan it and segment it out and all that other nonsense. So yeah.
Awesome. So before oh yeah, so there is a follow-up question actually. So very cool, thanks for the answer. Interesting that actually follow-up comment. Very cool, thanks for the answer. Interesting that the middle 50% of muscles is kind of the same. And yeah, CT is always wonderful, but lots of time.
Yeah.
Yeah. So before let's say ending the conversation, unfortunately, I just put in the chat the link to the seminar series. So next week we are not going to have a seminar, but we are going to have another one on December 8th by Dr. Moulton from the Mathematical Institute at Oxford. So everybody's welcome to join us. And maybe there is time for one last question. One last question. Well, if not, thank Dr. Astley again for the great presentation. Thank you very much.
Wonderful. Thank you.
Thank you.